Hi everyone. Welcome to the Dora Dōjō bounty presentation. We're gonna today have a workshop on a Halo2 ZK knowledge proof framework. But before we start, I want to quickly introduce you to Dora Dōjō community and Dora Dōjō bounties. Dora Dōjō is an open source knowledge community focused on cutting-edge technologies such as encryption and Web3. It's co-built by hackers and for hackers. On the Dora Dōjō website, you're going to find a lot of bounties on various topics, including scroll and polygon ZK EVMs, aptos, zero knowledge proofs, and many other things that are on the front end of the technology. And you can take on these bounties, prepare a live knowledge sharing session in form of a broadcast like the one that you're watching right now, or an audio or a text. So we highly encourage everyone to join and to share the knowledge, explore the frontiers of the modern blockchain and IT technologies, and win the bounties. So that was the short introduction, and now we're gonna start exactly one of the bounties, explore one of the bounties listed on the website, and this one is Halo2. So let me run the presentation. So my name is Alexey, and today we're gonna talk about Halo2. Halo2 is a framework for developing zero knowledge proofs and is one of the most widely used, robust frameworks today. So our agenda for this session is to have an overview of the Halo2 main ingredients, which is an arithmetization scheme, a commitment scheme, and an accumulation scheme. We want to develop a good intuitive understanding of how the schemes work, what they are doing, and how they do this. Next, we're gonna walk through a simple examples of how these schemes are involved in constructing the circuits. And we're gonna look at the examples, talk a bit about the examples on how Halo2 is powering ZK rollups for the layer 2 blockchains today. That's one of the main areas where Halo2 is being used today. And finally, you're going to have a chance to ask questions, and I'm more than happy to answer them. So let's start with a short overview. As I previously mentioned, Halo2 is a ZK knowledge proof framework written in Rust. It was originally developed by Electronic Coin Company, and it was developed for Zcash, a privacy-protecting digital currency. As the name implies, Halo2 is the second version of the framework. And because the zero knowledge field itself is a pretty young one, actually the first version was developed in 2019, and soon the second version appeared that had one major difference. One of the key components, which is the snark itself, so succinct, non-interactive argument of knowledge. In Halo 1 was Sonic, which was one of the first universal snarks. Universal means that this snark doesn't require any trusted setup. So it can be used for any computational problems and doesn't require any trusted setup before it can be used. And And in Halo 1, the problem was that Sonic was pretty slow, and in Halo 2, it was replaced with Plonk, a much faster snark that is currently on par with one of the fastest non-universal snarks. So it is universal, it can be used for any computation, and it's extremely efficient. So why Halo2 is one of the most powerful ZK snark frameworks in existence right now? It has two key properties. First of all, it requires no trusted setup. If you have ever read about or saw my previous, for instance, talk about Growth 16, one of the problems with Growth 16 and many other snarks is that they require a trusted setup. What does it mean? You have to trust someone to generate global parameters in a way that they discard secret values they used to generate it. If these values were not discarded properly, then the whole system was compromised and the prover can create fake proofs. So that's why having no trusted setup is very important in terms of the applications and the security of the ZK systems. The next important component that makes Halo2 powerful is that it was specifically designed to support so-called recursive proofs. In a nutshell, recursive proof is a proof of a proof. So instead of proving that we know a certain fact, a certain statement, or we performed a certain computation, we prove that we know a proof that this computation was performed. And we're going to see today how this can be applied in real life problems, for instance, in layer 2 blockchains, and why it is important. Next, it's one of the most highly optimized and well documented and well tested frameworks. There are many frameworks right now, but most of them are, let's say, in a very early stage in their alpha versions, and probably they weren't well audited at the moment. And one thing that sets Halo2 apart is that it is used live in many projects. It has been properly audited and properly tested. So it's robust and it's efficient. Taking this into account, we're now going to quickly look at the 3 ingredients that I've already mentioned in the agenda slide. And we're going to see later on these ingredients in more details and how they work. Again, these are the arithmetization scheme, the polynomial commitment scheme, and the accumulation scheme. So first comes the arithmetization. It's probably one of the most important things for any ZK system developer to understand, because it greatly affects the way you structure your circuits, the way you write your ZK programs. Knowing how arithmetization works and what can and cannot be done allows you to optimize your circuits. So basically, an arithmetization is a way to convert certain relations and so-called satisfying witness. So a witness is a private data, a piece of private data that the prover knows. Most often, it's a computation trace. So it's basically a number of statements that were executed during the computation. And we take these relations, this constraint, and this computation trace, and convert it into low-degree polynomials. So this idea underlies most of the ZK snarks in existence today. So we convert computation into a certain form that efficiently encodes computation. And usually this is either polynomials or matrices and vectors. Why polynomials is a good choice? Because there is so-called Schwarz-Zippel lemma. Again, it's a very simple lemma. We're gonna not probably discuss it today, but it's fundamental for most of the snarks. And it quickly allows us to test that a polynomial is identical to 0 in a probabilistic way. And for this lemma to work, we need to have a low degree polynomial. So if the degree is high, let's say the order of 2 to the power of like 256, this lemma won't be applicable anymore. For Halo2, we're going to look at how Plonkish arithmetization works. So Halo2 relies on so-called Plonkish arithmetization. And this arithmetization is converting your execution of the program, the traces and the constraints into polynomials. If you are familiar with Growth 16, you might remember that Growth 16 has another kind of arithmetization called R1CS, rank 1 constraint system. And it's basically converting everything into the matrices and vectors. Okay, so that's the first ingredient we're going to look at today. The second one is the polynomial commitment scheme. So on the first step, we took the execution and the witness and turned them into low-degree polynomials. Now we need to bind, as a prover, we need to bind ourselves to the polynomial and provably evaluate it at an arbitrary point. So by binding, I mean that we are committed to the polynomial. We cannot generate two different openings at certain points for one binding, for one commitment that we have. And we only want to prove that we know the value of the polynomial at certain points. Halo2 uses inner product argument as their polynomial commitment scheme. Just to give you an example of a different commitment scheme, so you have an overview, what else is there. There is so-called Plonkish, which is another Plonk-based framework, and it uses FRI, Fast Reed Solomon IOP. IOP stands for Interactive Oracle Proofs, which is a different sort of polynomial commitment scheme. And in the previous talk, I've thoroughly covered so-called KZG commitment scheme. You can look it up on the Dora Hacks YouTube channel and see exactly how it works. Again, for Halo2, it would be inner product argument. And the final step is so-called accumulation scheme. Again, this is something that makes the Halo2 so cool. It enables recursion of proofs, a proof of the fact that we know a proof. It has many important applications, and one of the probably most obvious is so-called streaming proof generation. And let's quickly take a look why it is important and how it is used in practice. So, as you may or may not know, a lot of ZK research stems from the blockchain development. And one of the key ingredients for scaling blockchains today is so-called rollups. So rollups are layer 2 blockchains that are built on top of the other blockchains. Often it's Ethereum and the rollups that are built on top of that. And you may know the rollups like Arbitrum, Optimism, and this one are so-called optimistic rollups. But there are also more secure, more efficient ZK rollups. An example of such a rollup is Scroll, ZK Sync, Polygon ZK EVM rollup. So what these rollups do, they basically scale the blockchain, the layer one, the underlying blockchain, by doing computations off-chain and then submitting them to the chain. And obviously, because submitting something to the chain is expensive, we need to spend gas to perform this operation, to store data and to verify data. We want to generate so-called state transition proofs, so proofs of the execution, not for each and every transaction, but we want to generate them and submit them in batches. Let's say that we pick a batch of 100 transactions and we decide to submit 100 transactions in our rollup to the L1 blockchain. The problem is that we need to wait while we acquire these 100 transactions, then we need to generate the state transition proof. So we need to generate a proof that these transactions were performed correctly and they changed the state of the layer 2 rollup. And only then we can submit the proof to the L1 blockchain to be verified. And obviously, because we have to generate a proof for 100 transactions, that can take a long time, which is not what we want. We want the proof generation to be as efficient as possible. How recursive proofs can help us? Recursive proofs allow us to generate much shorter proofs for sub-batches. So instead of waiting for 100 transactions, we take smaller batches of 10 transactions and we generate proof for these batches. And we can do this in parallel. So for instance, if generating the proof pi1 takes a lot of time, it's fine. We are still computing the next state, and we can generate the proof pi2 in parallel. And when we have all the 10 proofs for the larger batch, we generate the final proof that is going to be submitted to the layer 1 blockchain, which basically proves that we know the proofs, that the proofs are the correct one. So in this way, we have the recursion, we have the proof of proofs. Okay, so again, to sum up, Halo2 in a nutshell is Plonkish arithmetization, inner product argument as the polynomial commitment scheme, and incrementally verifiable computation prover as the part of the accumulation scheme. Now we're going to look at how these things work out in more detail. And we're going to start with arithmetization. In the original Plonk white paper, the authors introduced so-called vanilla Plonkish arithmetization. It starts with the arithmetic circuit. So that's the very common structure that most of the ZK snark use as the computation model. So how do we look at this? We see that there are gates and the wires put in values into the gates. And we have two gates, the addition and the multiplication. So we read this as follows. The first gate takes two inputs, performs addition, then sends the output as an input for the second gate, which is a multiplication, which multiplies it with the third input. And the result is emitted through the output wire. So there are input wires, output wires, and intermediate wires. The original Plonk paper had a single equation that allowed us to encode so-called local consistency checks. So local consistency checks are checks that show that each gate worked as it's supposed to work. So for instance, if we have the addition gate and W sub 0 is 1, W1 is, let's say, 2, then the output should be 1 plus 2, 3. So again, we are concerned only with the local correctness of the gate execution. This equation has two distinct components. Like the first one are so-called selectors, QL, QR, QO, QM. Selectors are defined on the level of a circuit, so they are hard-coded for a circuit. And then we have the witnesses, so the data that comes in and the output results of the computation, XA, X sub B, X sub C, XA, XB, 2 times more. And they depend on a particular execution. So the first thing is that we need to check that the gates are combining the witnesses and performing computation properly. So let's see how vanilla Plonk equation does this for us. The idea of the selectors, so this is the equation, this is the circuit. The idea of selectors is that they allow us to pick one of two operations, addition or multiplication. And that's important. In the vanilla Plonkish arithmetization, there are only 2 types of gates. You can either add something or multiply something. So selectors can take only 2 values. It's either 1 or 0. And let's say if we, it's actually very easy to kind of memorize the meaning of the selectors. So you can see this as the left and the right inputs, and the selector then picks the left and the right input to the addition. So it's either the left or the right. You can have the output selector, Q sub O, which is the result of the computation. And because the multiplication doesn't have the, you just need one selector for multiplication, additional, because it works differently. It's not the addition, yeah. Then you have one additional selector for multiplication. So let's look at some simple examples. So if we want to add XA and XB, we basically set the selector for the left input as 1. So we enable the left input. We set the selector for the right input as 1 as well. So we enable the right input. And then we want to make sure that these 2 values, XA and XB, sum up to C. So it means that we subtract C. Yeah, if we subtract C, then we should get 0. And that's why we pick as a selector here -1. Yeah, so we can also have -1. So not only 0 and 1, but also -1. So in a nutshell, it reads like x plus y plus xb, xa plus xb minus xc equals 0. And we remove the multiplication because we set the selector for qm as 0. Again, on a simple example, if we have to add 2 numbers, 2 and 3, we put the corresponding selectors to 1, and we subtract 5 using the output. So the output is 5, and that's why 2 plus 3 minus 5 should be just 0. In the same way, we can do multiplication. We basically just need to turn off the 2 selectors for the addition and just enable the multiplication. And the result is always subtracted to give us the 0. Again, it's a very simple way to turn local checks that the gates worked fine into the polynomial equations. However, there is another important piece. While the gates themselves might work well and be consistent, it's important to have the global check that the wires connecting the gates are doing this properly, so that the result of the computation from the one gate is routed to the another gate, and this is consistent. So we need to have the way to check so-called global consistency. In trusted setup snarks like Growth 16, this wiring is a part of the trusted setup, so it is baked into the setup. But in Plonkish, in Plonk and Plonkish snarks, we can do this in a universal way using so-called permutation argument. So let's look how it actually works. Again, this part is a bit technical, so we're going to look at the idea and then we're going to leave out some technical details. So our goal is to verify that two gates are connected properly. So the output of the addition is the input to the multiplication. We can represent the gates and the wires as the table, with the wires being the columns. So W0, W2, W1, W2, and the final column is the gate itself. Again, so W1 is the left input. We can call it left input, for instance, or the first input. W0 is the left input, W1 is the second input, and W2 is the output gate. So we need to make sure that these two values, so W01, so the input to the input value to the multiplication gate, equals to the output value of the addition gate. And the trick is, again, to encode it in polynomials. But this time we encode columns and we make them so-called Lagrange polynomials. So Lagrange polynomials are polynomials over the powers of the nth root of the unity in the field. So what does it mean? If we have n root of the unity in the field, when we in the finite field, when we raise this element to the nth power, we get 1. Again, this works in the finite fields, not in the regular real numbers. So we encode the polynomials in a way that if we take a certain column, an eth column, and we pick the jth row, then this polynomial wi of omega, the omegas are the nth root, to the power of j, again, j is the row, should give us the value in this table. So again, these polynomials are just an easy way to get the value, the indexed value, in the rows that we have in the column. So this is I is the index of the column, and j is the index of the row. So what is the idea behind the permutation argument? In order to enforce the equality of the wires, we can say that if we swap these two values, it doesn't change the polynomials. So remember, we talked about Schwarz-Zippel lemma that allows us to check that the polynomial is 0. So it also allows us in this way to check that the polynomials are equal. So we say that by swapping these two, the polynomials that we were committed to are equal. And this way, we say that the wiring of the circuit is correct. So again, swapping two values doesn't change the polynomial, means that these values are the same. Yeah, so that's the idea behind the permutation argument. The next thing that was built on top of the vanilla arithmetization, vanilla Plonkish arithmetization, is so-called custom gates. So custom gates are used in Halo2 to enable gates that have arbitrary linear combinations. So you can have gates that are not just the sum and the product, but for instance, the square of a certain value. So we can have a gate Q subsquare, that basically checks for us that if we square the input, we get the output. Or we can have a gate that only checks that the input is 0. So we take two values, multiply them, and subtract itself, the value itself. So this is the so-called 0 or 1 gate. This is a powerful construction that allows developers to have custom gates and work at a certain cost. Obviously, it's not for free, but work with a higher level of abstractions when developing the circuits. And the final improvement that was also introduced later, so-called ultra-plonk, and it's also used in Halo2, is the idea that we can pre-compute values for certain ZK unfriendly or computationally expensive functions. For instance, most of the hash functions developed before like ZK become an active area of research, ZK snarks become an active area of research, they are quite hard to encode as these circuits. So they require a lot of gates. So for instance, SHA-256 or Kachak-256 are requiring like thousands, hundreds of thousands of gates to be computed, which is very expensive for ZK computations. Instead, we can create a pre-computed table that matches the values, the input values and the output values of the computations that we want to that we can perform outside the circuit and just encode as the lookup table. And the idea is that if we have this kind of lookup gate that tells us, okay, this is the computation that has been done outside the circuit, this computation must be in one of the rows in the table. So this way we just extract the computation expensive things outside the circuit and just encode them. Okay, so again, the idea behind how it is implemented in practice is similar to the permutation argument. In permutation argument, we basically say that there must be two values that we can permute, and there are not changing anything. So here we say things that is a bit more permissive. We say that in every pair of the input columns that have the lookup, there must be equal to some pair in the table columns. So there must be a pair T1, T0, T1 that corresponds to the input. Okay, so as a result of the Plonkish arithmetization, the Halo2 constructs a large matrix with n rows and m columns, and each cell of this matrix contains an element of the finite field. The column corresponds to the polynomials that we have in the Lagrange basis, and the rows are indexed by the primitive roots of unity that we discussed. So if we take the polynomial for the column J and we put the omega I, which is the ith roots of unity, we're going to get the value, evaluate this polynomial at a value contained in the cell x, y, j. So ith rows and j's column. As you may have already noticed, the matrix itself has three different segments. So we can have public inputs, so-called instance columns in terms of the Halo. These are the values that both prover and verifier know. There are also private inputs, or the witnesses, the computation witnesses, that only the prover knows. This is the red part. And finally, there are fixed columns. These are preprocessed values, selectors, lookup tables that depends on the circuit and the lookups we want to have in our ZK program. Let's take a look at a specific example of how a simple computation might be encoded in this way. So we're going to look at the Fibonacci sequence. Fibonacci numbers are, as you may already know, are the numbers that are defined as follows. So we start with 2 ones, and the next number is the sum of the two previous numbers. So for instance, if we have 1 and 1, like two fixed initial numbers, the third Fibonacci number is 2. And the third is the sum of the previous two. So 1 plus 2 gives us 3, and so on. So a ZK circuit that compiles, that calculates Fibonacci numbers for the first 5 numbers might look as follows. We have the input 1, which is the initial number we need to start with. So with the first, we start with the first Fibonacci number. And we have the output 13, which is the result of the calculation. Thanks to the Halo2, we can define our own type of gate and selector called QFib that sets a constraint to how the computation is performed. So we take on each row, on the current row, we take the zeroth wire, the first input wire, we take the second input wire, we sum them up, and we make sure that it equals the output. So again, in the Plonkish equation, we're going to have QFib multiplied by A0 current plus A1 current minus A2 current. And that should equal 0. This constraint makes sure that each row, this calculation on a row is performed correctly. Obviously, we need to have more local constraints. So we can see that because the second row, each next row starts with the same number, the sum of the two values on a row must also be equal the first value on the next row. So again, we are shifting rows right now. So we have a local constraint that works in the vicinity of the current row. So we work with the current row and with the next row. And in our case, we're going to say that if we take the first input of the current row, add the second input of the current row, it should be the same as the first input of the next row. So first, second, first on the next row. Not on the current, but on the next. And this should hold. And this constraint should give us 0 if we have the QFib selector. So we are calculating Fibonacci numbers here. So these are local checks. They are always either in one row, or they use the offsets relative to the local row, local context to calculate, to constrain gate results. One more example of a local check that we need here is that, again, if we pay attention, is that this sum, 3 and 5, 1 and 2, should equal to the first wire on the next row. So in a similar way, we set up one more local constraint. However, there are certain constraints that must hold for this computation to be verified by a verifier that are not local. So the first one is that if we end up on a row with a certain number, like here with 2, we need to start with 2 on the next number with the same value. This can be encoded as a local constraint still, but again, if we start looking at how rows are interacting with the inputs and the output values, we're going to see that it's becoming harder and harder to perform local checks. We're going to have to add more types of selectors, and the whole circuit will, the whole matrix will grow. So this is exactly why we need so-called permutation checks that we discussed briefly before. That basically informs that we copy the values correctly. No computations are performed, but the values are correctly copied. So the first constraint is that if we end up with a certain number, we start the next node with the same number. And these constraints, the final 3, are for the inputs and for the outputs. Again, permutation checks, we're not going to have a deep dive here, but permutation checks result in more polynomials to be generated, but in a slightly different way. Okay, so now we have the polynomials for the local checks and for the global checks. We need to be able to commit to these polynomials so that the verifier can test us by opening the commitments and checking our proofs that these are the polynomials that define the computation. So how the polynomial commitments work. As a prover, we pick up we have a polynomial or a set of polynomials, and we submit to the verifier the commitment. And then the verifier can test us at a certain random point, asking us to evaluate the value of the polynomial at a certain point x. And we, as a prover, need to send the computation result, so the y, the value of the polynomial at the point x, along with the proof that f of x is y and f is a certain family of polynomials. And the verifier can check that and either accept or reject. So for the commitment scheme, Halo2 uses so-called inner product argument. This is different to many others many other commitment schemes. For instance, the Halo2 version from Privacy and Scales Exploration. This is the research organization that also works on developing Halo2, but it's a fork of Halo2, uses KZG as the polynomial commitment scheme. Plonkish, which is another Plonk-based framework, uses FRI. Let's take a look at why and how the IPA, inner product arguments, are used as the polynomial commitment schemes in Halo. Again, the idea is that after the arithmetization, we commit to the polynomials that we get, and we construct so-called vanishing argument. So vanishing argument is basically an argument that certain polynomials are zero. And this is exactly where this low-degree Schwarz-Zippel lemma comes into play. Then the verifier evaluates the polynomial at a certain point, and we construct the opening that can be checked with respect to the commitments. What is the idea behind the IPA, inner product argument? So inner product is the product of two vectors, basically, that gives us a scalar. So we multiply them component by component, and we get the scalar value. Originally, inner product argument was used for vectors for a prover to convince the verifier that it knows the vectors with the inner product given to the verifier. However, if we pick one of the vectors as the powers of some numbers, the inner product becomes the evaluation of a polynomial. So we basically, instead of just multiplying vectors, we can look at it as an evaluation of a polynomial. The idea of the inner product argument is similar to the construction of the bulletproof snarks. It's basically a divide and conquer algorithm. When we start with the two vectors, A and B, we divide them and we construct proofs for commitments for smaller and smaller vectors until we get down to the trivial commitment that is easy to check. We're not going deeper into the algorithm. It's pretty involved. And there is a separate bounty, by the way, on the Dora hacks that is exactly covering the IPA. And hopefully we'll have a separate talk about this construction later on. But it's important to understand why IPA was actually chosen, because the problem with inner product arguments that while they have relatively small proof sizes, the verification tie is very high. It's linear, which is usually not good for snarks. But the reason why Halo2 specifically uses inner product argument is that this iterative structure, then we start with something big and we apply iterations by dividing the larger problem to a smaller one, helps us to merge, multiple inner product argument proofs into one. So this comes in handy because Halo2 is specifically trying to solve the problem of recursive proofs. And recursive proofs are, as we discussed previously, are handling the problem of adding proofs to other proofs. So if new things, like transactions on the blockchain, are appearing and they need to be proved, we can just keep taking the existing proofs and adding new proofs to them. And this allows us to amortize away the linear time, because we can verify many proofs at once at the end. So verifying each and every IPA proof is costly. But by aggregating a lot of proofs and then verifying them at once, this becomes less of a problem. In fact, it becomes constant, but still higher than, for instance, KZG. So for a large number of proofs, we don't have this linear verification time problem anymore. Sorry. Okay, so that brings us to the last part, the accumulation scheme. Again, the accumulation scheme is something that enables recursion for us. And the idea is pretty simple. It turns out that it's much cheaper to combine two proofs in a constant size accumulator, and it takes the logarithmic time. Then we can delay the validation, which is expensive, this linear time IPA verification, and only then spend linear time checking the proof. And this is so-called incrementally verifiable computation scheme that is underlying all kinds of ZK EVM virtual machines nowadays. So let's take a look how it works as a bigger picture. So let's say we have a prover that needs to generate the proofs, and it has the constant flow of the state transitions. So something new is coming. So we have a new input to the prover, Zi. We have a certain function that performs the state change, and we have a new state, Zi plus 1. Imagine that this is like a current state of the blockchain. Here we have a transaction and the virtual machine that performs the transaction. And we have the output, the new state of the blockchain. So what the prover does is that it, first of all, accumulates the proofs for all the proofs that we had before. So we had the input, Zi, we have the previous proof, pi I, and we had a previous accumulator state, AI. And there is a way to cheaply accumulate these proofs. So whenever a new transition happens, we can generate a new snark for the transition and accumulate it in the proof. So we have the new proof for the incremental change pi I plus 1 that will go into the accumulator again on the next step. So we can prove many small transitions and accumulate them in one constant size. It won't be large, constant size accumulator. Finally, when we have the accumulator and we want to verify the whole batch, all we need for the snark verifier to have the accumulator, the final accumulator, the last proof, pi I plus 1, and the last state that we need to verify. And then we're going to verify all the iterations of the proofs that we had, all the recursion of the proofs at one run. So IVC verifier checks the accumulation, and all proofs are checked at once. It takes linear time, but you don't have to do it on each step. It can be executed once for a batch. So again, Halo2 is, because of this property of being good at recursive proofs. It's widely used in blockchains for blockchain and the digital currency Zero Cash. It powers the recent development of many ZK virtual machines, Ethereum virtual machines such as Scroll and Tyco. Both are in the testnet. And it's also used by Axiom ZK processor, which provides smart contracts with trustless access to historic on-chain data. And this is already in the mainnet. So Halo2 is widely used in production and is considered very robust. As I already slightly mentioned, there are different variations of Halo2. So one of the most common is so-called Halo2 privacy scaling explorations. And this is the fork with a few notable differences. It additionally supports KZG, which is especially good if you don't need to have recursive proofs. It supports dynamic tables. So we looked at the fixed tables for the lookup, but there is nothing that stops Halo from extending to support dynamic tables, and this version of Halo supports them. And it also has so-called challenge API. So privacy scale and exploration versions support multiple rounds of commitments and challenges. One of the also important differences is that while Halo2 from privacy and scales explorations is more rich in features, the original Halo2 has been more audited and more, let's say, considered more secure. Finally, let me add some more references. In this presentation, we looked at certain examples that I've taken from the Halo2 Applied ZK Learning Group by ZeroXPark, which is a great resource, and I highly recommend everyone to look at. Some of the examples and more detailed exploration of Plonk can be found in ZK course on zklearning.org. And for those who are willing to deep dive into the Halo2 architecture, I leave some more links on the different aspects. So arithmetization, IPA, IVC, they are all require their own workshops to work through in more details. And the last but not least, I highly recommend you to try and implement your Plonk prover and verifier from scratch. There is a nice template for this from the MIT course Modern Zero Knowledge Cryptography, and this is a nice exercise, practical exercise in Plonk that will help you to better understand how Halo2 works. That's basically it. So we looked at the structure of the Halo and the main ingredients, main components that make it work and make it one of the most robust and high performance ZK frameworks. If you have any questions, feel free to ask them in the chat. I'll be happy to address them. Okay, there seems to be no questions at the moment. Yeah, so don't hesitate to ask questions on the Dora Hacks forums, and just I'll hope that I'll be able to answer it there if you have any. If you watch this in recording, visit Dora Hacks and join the community. So thanks everyone for listening, and hope to see you again on the next workshops on zero knowledge. Have a nice day, guys. Bye-bye.